Hello and welcome to another bioinformatics video where I will be talking about BLAST, the basic local alignment search tool. But first, some review on basic programming. How do we fetch all but the last item in this array? And we're given an array here, np.array, and it's got some numbers in it. And the idea is we want to fetch a range from the first element here all the way up to the second to last element, omitting the very last one. And if we look at the options here, we'll see that the first choice here does what we want it to do. This colon here indicates that we're creating a range, and this will start from the beginning. If we don't provide any information, it'll assume we mean the beginning, and it will go up to, but not including, whatever number we put here. And in this case, we put a -1, which indicates that we want the last item in the array. So this then would select the range from the beginning up to, but not including, the last item. In fact, the second choice here is also correct. This one is basically the same, except that it is explicitly including 0 here as the beginning of this range. And this will do the exact same thing as A. It will take a range from 0 up to, but not including, the last element, -1. And then C, and then C here is also doing the same thing. So if we count the elements, we see 0, 1, 2, 3, 4, 5, 6. So 6 is the last element, and it has the same meaning here as the -1 here in the context of this particular array we're looking at. So a range from 0 up to, but not including 6 would also fetch us all but the last item here. So the correct answer is all of the above. How would we print out each element of this string? And we're given a string here, ATGTG, and the task is to print out each element. So option 1 here is a for loop for I in my string, print I. So this will work. I, the iterator, will take on the values that are provided in the list we give it. Or in this case, it's not a list. Another type of sequential data, a string, basically a list of characters, and I will be A on the first round through, and then it will be T, and then it will be G, and so on. So if we print out I each time, then this will absolutely work to print out each element of the string. What about option B? For I in range 0 to the length of my string, print my string, and in brackets I. So in fact, this will work as well, right? Because we have I, which is taking on the elements in this range. And this range is going to have numbers like 0, 1, 2, 3, 4, just counting up from 0 and incrementing by integers by 1 each time, up to the end of the string, or as many integers as there are items in the string, we will get a number line, a number range there. And so I, instead of being these characters, it's going to take on the values of those numbers. But then what we do is we can print out, reference the position using this iterator with numbers to fetch the items in the string stored at each location. So on iteration 0, I will have a value of 0, and we'll print out the character that's stored in position 0 of the string, which would be an A. On iteration 1, I would be a 1, and we would print out whatever is stored at position 1, or the T. This would continue until we get to the end. So this would also work to print out each element of the string, as the question asks. And then C, if we take a look at this, this is basically the same as B, except instead of supplying this range generator here, we are explicitly providing a list of numbers from 0 to 4 here. And it will do the same thing. I will be 0, and then it will be 1, and then it will be 2, and so on. And each time we will use that number as an index to fetch the character stored in the string. So the correct answer here would be all of the above. How would we retrieve the number 16 stored under item B from this dictionary? So a dictionary is a data type in Python which takes a key that you provide and sends back a value that is stored and associated with the key. And to make a dictionary, we use this notation here, where we provide first the key and a colon, and then the value. And it will always go in that order. So we have the key, whatever it is. In this case, it's a string, and that key is associated with the value, and not the other way around. So the way we fetch items from this dictionary is always by supplying a key and getting back a value. You wouldn't do it the other way around. If you wanted 10 to be your key, you would have to put that first here. And then you can provide, keys can be a lot of things. Keys could be numbers. In this case, they happen to be strings. Likewise, the values do not necessarily have to be numbers as they are in this case. They could also be strings. They could be lists. So the question is, how do we retrieve the number 16 from this dictionary? So we see that 16 is stored as the value for item B. So to fetch it, we would have to use the correct key as the input to this dictionary. So here we have my dict, and the correct answer is this one, C, where we provide, in quotations here, item B, which is indeed our key. The reason this is correct and not B, for example, is that the key here is a string. That's the data type. And in this case, we would get some kind of error because Python will understand that if we don't provide quotations, if we just provide a word, it's going to look into the namespace for a variable called item. And it probably will not understand the space here either. So this would produce some kind of error, whereas this one, it understands this is a string that is a key in the dictionary, and then it will retrieve whatever is stored there, in this case 16. So C is the correct answer. Which algorithm is appropriate for checking if two distantly related genes share conserved domains? And we have several options: Smith-Waterman or local alignment, Needleman-Wunsch or global alignment, or PAM250. So if two genes are distantly related, but they share conserved domains, it's likely that large stretches or regions may have different sizes, and that these conserved domains are not necessarily in exactly the same corresponding position. So this is a job for local alignment, right? Where we're accepting that maybe we have large regions of unaligned bases that we're just going to ignore basically and search for the regions that do align well. So that is item A here, Smith-Waterman or local alignment. Which substitution scoring matrix is appropriate for comparing sequences of high similarity? PAM350, BLOSSOM50, PAM250, or BLOSSOM80. So remember that in the case of PAM, the PAM substitution matrix is using a model of evolution, and we have this unit, right, which is one PAM, or 1% accepted mutations, or one accepted mutation per 100 amino acids. And this is accepted in the sense that natural selection has accepted the mutation. And the larger this number, the more PAMs, the more mutations have occurred in between sequences. And so this then becomes a measure of evolutionary distance. The greater the evolutionary distance, the more different the sequences are. So a higher number here is more appropriate for sequences of low similarity, whereas BLOSSOM, on the other hand, is the number that's coming after BLOSSOM, indicating which matrix. In this case, it's indicating the percent identity. So this is not this evolutionary model, but instead BLOSSOM is the numbers in the BLOSSOM table are generated first by gathering a bunch of sequences that meet a certain identity threshold, percent identity threshold. So if we gathered sequences that had just 50% identity threshold, this is not a very strict bar, right? A lot of sequences might get added in this case. In contrast, an 80% identity threshold is much stricter. So this is, so option D here is what is most appropriate for sequences of high similarity, right? Because the two PAM options are both for quite large evolutionary distances. These are barely related sequences. BLOSSOM 50 is going to let in all kinds of barely related sequences. So 80 here is the strictest of these options. So this is a scenario. An experiment produced this data here. So this is a next-gen sequencing data set. And a large majority of the material in this data set turned out to not be related to the target of the experiment. So only about 0.1% of these reads, these data points, contained the target sequence of interest for this particular experiment. And a question remained, what was the remaining 99.9% of the material? So in this situation, one would often do a blast experiment. So you can go to NCBI, the website, and go to nucleotide blast here. And similar to a search engine, you would enter in a query and then search for this sequence. And upon doing this, you get these different results. And they're ranked and scored according to their significance. And we get something here, which is like an E value, it's called. And this number is indicating how important or significant the results are. And in this particular case, an E value of on the order of 10 to the minus 16 is a quite significant hit. So we took from this result in this experiment that we had potentially identified successfully one of these unknown sequences in the remaining 99%. And it turns out this was some kind of phage DNA. So it was a close match to this bacillus phage Maceta. So the conclusion was that perhaps this was some kind of contamination that had entered into the experiment. And it was an experiment involving a lot of PCR amplification. So it seems quite likely that perhaps some small contamination got amplified and overwhelmed the rest of the sample. So BLAST is a very useful tool, and it utilizes databases, and searching in general we're relying on it a lot increasingly. Google, for example, is a very useful tool, and it's based on a search algorithm. And we have also a lot of databases available to us in biological research. And searching presents two problems. One is, how do we get two kind of conflicting problems, you might say. So one is, how do we get a really sensitive search? So how do we detect really distant homologs and avoid missing positive results? And then the kind of trade-off with this, but which we're also interested in, is having results be very specific. So we want to reject anything unrelated to our sequence of interest. And we want to be able to cover a lot of material. We want to be able to search a huge database and while avoiding false positives. So hits in a database are often partial and local. Also, the databases are huge, right? This is GenBank in 2019 had 212 million sequences. So this is a bit of a difficult problem, an optimization problem, especially considering that dynamic programming is very computationally demanding. So it's not going to work for us to simply run Smith-Waterman on 212 million sequences every time, especially when some of those sequences might be very long. So this problem needs to be optimized. And one of the earliest attempts to do so was with the FASTA local alignment algorithm. And this was one of the first of these kind of efficient methods that try to balance sensitivity and specificity. It was based on this observation that good alignments have short stretches of identical matches. And identical matches are much more computationally easy to detect, right? If you're not having to deal with gaps and checking many different combinations of how to space out your bases, your characters. And the first searches are for word-to-word matches in this algorithm. So you have something called a k-mer, which is just like a word, basically, of k consecutive bases. So for instance, you could have a 3-mer, and this would be a 3-letter word, right, where k equals 3. And the idea is that you're finding candidates for these identical matches and searching for local regions where you have many of these matches, like a high density of these identical k-mer matches with your target sequence. And then the algorithm then uses this density, these high density regions, to kind of connect them, and then use the Smith-Waterman algorithm to finish off the more promising candidates. An evolution, though, of this type of efficient algorithm came along in 1990 with BLAST. And then this is still actively used and maintained today. And it's kind of two things. It's first and foremost an algorithm, but it's also a tool which you can utilize both online by going to NCBI, as well as locally. You can download it, and you can download databases and run BLAST locally on your machine. And unlike Google, for instance, the code for this tool is open source, and the algorithm is published and known. So the general idea behind the algorithm is that we have some kind of sequence. This is called our query. This is the one we're going to search with. The query is broken into all possible k-mers, and k is usually 3. So it's broken into all possible 3-mers, and we make a list and check which of these 3-mers have an alignment score with a 3-mer. We check which possible 3-mers you can make that have an alignment score with the 3-mers from the query that we got in step 1, that have an alignment score that is above some threshold. So in like Smith-Waterman, for instance, the numbers that you care about are the match score and mismatch scores. Maybe you have like a substitution matrix for these numbers, or maybe you just have fixed match and mismatch scores and a gap score. But for BLAST, you need an additional number, which is this threshold. And the threshold determines which k-mers, in addition to the ones from the query, you're going to use in your search. So you're not just going to use the k-mers from the query, but you're going to use all k-mers that have a sufficiently high score, and just search for exact matches of those k-mers, of those 3-mers, in the database, so in the sequences that are contained in the database. And then when you find those matches, you extend them using a local alignment. And you do this until the score drops off by some value x, and then extract from that your hits, which are these high scoring regions that you've extended using Smith-Waterman. And then the most important step at the end is to evaluate the significance statistically because a lot of times you can get a hit, but depending on the parameters, the size of your database, the size of your query sequence, it may or may not mean anything at all. So here is a quick example. We have a query sequence, TGCA here. And the first step would be to break the query sequence into 3 mers. So in this tiny example, we just have 2 possible 3 mers, TGC and GCA. Oh, ignore this. That's wrong. Oh, yeah, there we go. And we are going to check all possible alignment scores of our 3 mers. So right? We took these ones, TGC and GCA, and we're going to find all possible other 3 mers out there that exist that have this this threshold. So if we look, and here we're just doing a very simple example, right, where a match is 1 point, a mismatch is -1. And here we can see that there's a match, and a mismatch. So this particular 3 mer would have an alignment score of +1 with our original 3 mer. So that would meet the threshold and go in. So in this particular case, we have already printed out all of the possible 3 mers that meet this criterion. In the case of proteins, like an amino acid 3 mer, like this CHH here, we would do the same thing. So we pick a threshold. In this case, it's 19. And we would locate all possible 3 mers that have an alignment score of 19 or better with CHH. So of course, CHH is going to have a perfect score, and 2 other candidates, CHY. So there's a mismatch between the Y and the H, of course. But if we look in a Blossom 62 matrix here, and we look up under H, and Y, it gets a +2 if we add those. So 9 plus 8 for the 2 matches, and then +2 for the mismatch. This scores 19, and this meets our threshold. So if Y had been something else, if it had been you know, let's see, H, and if it had been a W, for example, then we would not have made it up to 19, and we would not have included that 3 mer in our list. In this case, also CYH happens to meet the threshold as well. Then what happens next is, so you've got your list of 3 mers, then you go through the database and find locations where there are perfect matches. So you would populate the search with these seed points. And likewise for the protein version, same thing. So we're looking for identical matches wherever they occur. And once you've found these identical matches, you can display them, for example, in a grid like this. So in this case, here's our original query sequence and an example, a small example of a database sequence. And we get a match here, TAC. TAC is one of our 3 mers that we're searching for. And you can see, oops, you can see it goes here. Likewise, ACA here, TGG, and GGA. Next, the next step is to extend from these seed points using local alignment to try and grow the hit as much as possible. And the way this is done is, as long as the score is going up, you continue to include additional bases. Eventually, it may start to go down, and then you pick some cutoff point relative to the max. And then when you trigger that cutoff point, if it goes down, say, more than 5, the score goes down more than 5, then you would trim back to the maximum, and that becomes your hit. So here you can see this performing Smith-Waterman on the seed points and calculating these adjacent cells and doing trace back from the max to the origin. And in this case, then we have two blast hits for this particular sequence. And then another thing about the BLAST algorithm is that it's done extremely efficiently, which of course is really important for when you're performing billions of operations. And every bit, every little tiny operation counts. So one thing that is exploited is the fact that there is overlap. So when you're scanning a 3-mer along a particular sequence, at any point in time, the match you're looking at may be relevant to not just the exact frame that you're looking at, but it could overlap a little bit with adjacent frames, since it's a 3-mer and not a 1-mer. And so there's something called a finite state machine, which can be used to make this search efficient. And basically the idea behind it is, let's say we're scanning our sequence and we run into the base C in our database sequence. And we know that we're interested in these three mers, CHH, CHY, and CYH, and that a hit for any one of these would be of interest to us. So rather than searching the database 3 times for each of these, we could instead take note of the fact that they all share a C in the beginning. And then anytime we encounter a C, we are 1/3 of the way to potentially discovering one of these 3 mers. Likewise, if we run into a C and then we happen to run into an H, we have narrowed it down even more, and we know that we are just 1 base away from discovering either CHH or CHY, and at the same time eliminating the possibility of discovering CYH. And so you can kind of visualize this process on this kind of network here. And the system can either be in, for this particular set of 3 mers, the system can be in one of these 4 states. And if we're beginning a search, for example, just ignore these sequences here. If we're beginning the search, say, for CHH, CHY, and CYH, and this is our database sequence, we would start out looking at the C here. And the system, which doesn't see, for instance, anything that's going to happen downstream. So all it can see at this particular instant in the program, it sees that there's a C base here, and it knows that therefore it is only 2 bases away from potentially discovering one of our target 3 mers here. So the system moves to state 1, and state 1 is basically the state of being 2 bases away from discovering these 3 mers. So we indicate that here. The first step is to go to state 1. The next base is a Y. So a Y could potentially lead us to this last one here, CYH. And so we follow the Y arrow here out to state 3. And state 3 is basically being in the state of being 1 base away from potentially discovering CYH. And depending on what happens next, we might either discover CYH or have to go back to some other state after discovering that we did not find CYH. So what happens is we hit a C and we revert back to state 1 because CYC is not one of our options. But now we're back in the state of being potentially 2 bases away from discovering one of these 3 mers again. So you can just kind of follow this trajectory. So we run into a C, we go to state 1. We run into a Y, we go to state 3. we run into a C, we go back to state 1, we run into an H, and we go up to state 2 up here. And so you remember state 2 is the one where we're basically just one base away from potentially finding one of these guys. We hit a C after the H, and then we have to go back to state 1 again. And then we go to state 2 again. And this time, the algorithm finds a hit because the next one, of course, is another H. So then it moves back to state 0 through this exit condition here, or this emission event. And then it will discover a CHH and then go back to the state of having found nothing again and restarting the search with the next base that comes. Yeah. So, and these details may seem a bit arbitrary, but they are extremely important for increasing the efficiency of BLAST, which becomes very important when your databases are huge. And in fact, the efficiency of BLAST is much better than Smith-Waterman, so its runtime is proportional to the length of the query sequence times the log of the length of the database sequence, like the total length of all sequences in the database. And this is in contrast to Smith-Waterman, which is basically m by n. So this is a much bigger number. And if you think about that, this is kind of because in Smith-Waterman, you're calculating this matrix every time. And to fill it in, you have to do m by n number of operations, m times n operations, a rectangle's worth of operations. Whereas in BLAST, you're kind of more efficiently zooming in on the parts that matter and doing a more limited local alignment where it matters more. So that's all for this video. In the next video, I will talk about how evaluation of BLAST is done. So see you there.